Okay, one little new piece that's not galvanometers. I do know I'll need to come back to galvanometers in class to help you figure out what the heck I was talking about. The new piece we're going to talk about is called electromagnetic induction. It is in the second half of the unit. It will be on the second test, not on the first test. Okay, remember we talked about Hans Christian Ørsted and how he discovered that an electric current would produce a magnetic field, right? So he had a wire with a current in it, and he discovered it set up a magnetic field around itself. And he found that out because a compass needle moved when it was near it. Well, after he did that, there was a guy named Michael Faraday, and some of you maybe have heard of him just because there's Faraday's law, and there's actually a unit named after him. So if you took electronics, you probably heard of Michael Faraday. Okay, now Faraday thought, so if a current sets up a magnetic field around itself, then I should be able to show that a magnetic field can produce a current. Our universe is very symmetrical. So if a current produces a magnetic field should produce a current. This guy, he gets props for his perseverance. He worked for about 8 to 10 years trying to prove it. We're talking 1822 to about 1830. And he eventually figured it out. And then later that same year, a second guy, Michael Faraday was English, a second guy, Joseph Henry, who was American, also proved it. But Faraday gets the credit because he was first. Of course, you can imagine that back in 1822 to 1830, you could figure something out in England and no one would know about it in the States for a few months. So there was some controversy over who really do it first. Okay, so what Faraday wanted to do was he wanted to show that putting a wire in a magnetic field would cause a current to flow in the wire. So we know that a current carrying wire can produce a magnetic field. We know if we have a current in a wire and we put it in the magnetic field, it experiences a force. But he wanted to show if he took a wire that wasn't attached to anything and he put it in a magnetic field, that the magnetic field would produce a current in the wire. He eventually did induce a current in the wire, but he had to add one other little factor in. It will only create a current in the wire if you're moving the wire with respect to the field. Okay, and of course the rumor is he was giving up, so he would have had the wire hooked up to an ammeter. So he would see, right? So right now there's nothing flowing in it. And he did all kinds of things. He made the field stronger. He changed the orientation. He changed the material. But finally, it was when he moved the wire with respect to the field that the current flowed. Okay? So there will indeed be a current induced. Induced. Induced means it's brought about, that it wouldn't have happened on its own. You often hear about women who are expecting being induced. That means that doctors will start the labor so the baby will come. Okay, so induced means it doesn't start on its own. So he found that when a wire moves up in a magnetic field, the current flows one way, and that when the wire moves down in the opposite direction and down in a magnetic field, the current will flow in the opposite direction. But if the wire's just stationary, no current. So this is called electromagnetic induction. Okay, and it's when a straight wire moves with respect to a magnetic field. With respect to. What that really means is you can move the wire in the field or you can change the size of the field. Like you could so you could either change the field or move the wire. So when a straight wire moves with respect to a magnetic field, there's a current induced. The size of the current will depend on the rate of change of the magnetic field. Okay? The rate of change might be because the wire's moving up and down quickly, or it might be because we're moving the magnets out or in, right? So it's dependent on it could be created by two things: moving the wire in the field or changing the strength of the field. And what Faraday found was that the current will always flow in the wire in an attempt to counterbalance the change. So if I'm moving this wire out of this magnetic field, the wire experiences the field getting weaker, and it doesn't like that, so the current flows in the wire to try to make the field stronger again. If I move the wire down into the field, now the field's getting stronger. The wire doesn't like that, so it'll set up a current inside itself to flow in such a way to try to make the field weaker. So it's one of those, like those people that you might know that no matter what the change is, they don't like it. The wire is the same idea. So we're going to have an equation here. Oh, actually, so as a result of the flow of the current, then you get a voltage produced, a potential difference produced in the circuit. Okay, now back in the olden days when they were doing this, they thought that what was produced was, or what was creating the current was a force. They thought that as you moved the wire, then you were creating a force. Remember, a wire in a magnetic field has a force acting on it. So they thought that by moving it, they were creating the force, and that force was then pushing the charged particles through the wire, creating the current. So they called this force the electromotive force. Okay? Electromotive, also known as EMF. Now, what do you think this EMF is going to be dependent on? We're going to get an equation for EMF, and the EMF is actually dependent on 4 different things. It's going to be dependent upon the field strength, how strong the field is that the wire's in. Okay, so it's going to be dependent on B. It's going to be dependent upon the length of the wire that's in the field, how much wire's in the field. It's going to be dependent upon the speed with which the field's changing or with which you're moving the wire, and it's usually moving the wire. And then it's going to be dependent upon the angle between them. Okay, and so the bigger the magnetic field, the bigger the EMF. The more wire in the field, the bigger the EMF. The quicker you move the wire, the bigger the EMF. And the angle, well, so it's going to be EMF equals B, and it's really going to be, BVL. I'm going to change that. EMF, electromotive force, it's a vector. And so it should be sine theta. Okay, and so we get EMF, we usually write it as BLV, sine theta. I was pausing just because I was thinking about something else. We switch this, maybe because it's easier to remember because it's like BLT, okay, electromotive force. Now, when you come back to class, I'll talk about this more. But one of the things I want you to do this evening is to prove the units. Okay? And you might have a little trouble, so don't stress. We'll look after it when you come back. The second thing I would like you to do is to try, there is a hand rule with this, but I'll do the hand rule in person. Try on page 518, numbers 1 to 4. Okay? And again, don't stress if you can't prove the units. We'll do them when you come back. Okay? All right. Have a good one.